All right, I got 1 o'clock, shall we? Any questions about anything before we dive back in? Okay, so we left off in the middle of section 1.2. So far what we've focused on is reducing matrices to solve equations. So reducing matrices in a couple of different ways. And I think the last system we looked at last week was the only one where we couldn't find a unique solution. So in this case where we have infinitely many solutions, we can still talk about what those solutions look like. We can still talk about the relationships between the variables, even though like z is the only one that we found a very specific value for. So here are the two big ways we talked about reducing matrices. So similar names, row echelon form, and then reduced row echelon form. So similar names, but there's one very key difference between them. What is the difference between these two things? These both came from the same matrix. But what's the major difference? Go ahead. Right. So the first thing we looked at was to get in this, basically get zeros below this diagonal. So these both have that feature. The big difference is that in Gauss-Jordan elimination or reduced row echelon form, wherever possible, we get zeros above that diagonal as well. It's not always possible, but where it is possible to get those zeros as well. But like we talked about last time, it's not always possible. Sometimes you're not going to have a unique solution. So like in this matrix here, how many variables do I have for the equation, the system this represents? 4, and how many equations? 3. So there's no hope of getting a unique solution. So let's go a little further. Actually, I think we might have done this last time because, yeah, we finished this system. So let's look at a new one. So put some formalities behind kind of the way we're parameterizing these solutions. So if we talk about a pivot, that's basically any column that has, a leading variable. So all these ones here, these are pivots. And that coincides with things we call lead variables. So when we start quantifying our solutions here, or start naming our solutions, so let's say that these variables are w, x, y, and z. What can we say about our solutions for this system right now? Go ahead. Z equals -4 and y equals 1. So those have concrete values. What can I say about w and x? Is there any relationship there? But w plus x equals 17. W equals 5x equals 17. So in this case, the lead variables are w, y, and z, and then a free variable. The only free variable here is x. So if I isolate w here, what do I get? I get w is equal to 17 minus 5x. So we talked about this last time. We have an infinite number of solutions for this system, but we can still be specific about the conditions we have to meet to have one of those solutions here. So y and z, the conditions are very clear there. W and x can be related in some way, but there's an infinite number of ways to satisfy those. And we always assign free variables a parameter. So something you probably, if you've kind of looked at the affinity, you've probably seen something like this, 15 minus 5t. or whatever their favorite parameter to use there for x equals t. Any questions so far? Okay, so let's take a look at one here. So how many variables am I looking at now? 5. I don't have enough equations to represent them, but let's try to parameterize as much as we can. Yeah, are we okay with that matrix? Can we reduce it any more than it already is? I don't think so either. So how many pivots do I have? Or lead variables? 3, right? What are they? Well, yeah, so the pivots are always, when we reduce, the pivots are always going to be 1. What are the variables that they're associated with? X1, X3, X5. X1, X3, X5. So basically, in every row, where do you see the leftmost 1? Or the leftmost non-zero value if you haven't totally reduced? So those are going to be our lead variables. So basically, when I write our solutions out, we're going to have x1 equals something in terms of other variables. Same with x3 and x5. x5, I think we can probably square away just as -6, right? What about x3? Do we have anything? Go ahead. Go ahead. -1 minus 2x4. All right, and then what about x1? Or more, how did you get that for x3? How'd you get -1 minus 2x4? Okay. Right, so we got isolating x3. We can do something very similar with x1. What would that give us? Plus x2 plus x4. And then if we want to assign parameters to, how many parameters do we need? 2. So I can't assume that x2 and x4 can be controlled by the same parameter. So x2 equals s, x4 equals t. And then I'll say this, x1 equals -3 plus s plus t. x2 equals -1 minus 2t. x5 equals -6. So I think I have to package all this to talk about what my solutions are. So there's an infinite number of solutions, and in this case, I have a couple different degrees of freedom to get all of them. I have 2 different parameters that are completely independent of each other, which is why I have to call them different things. Makes sense. How we doing? All right. Can we go again? Tell me what to do. Okay. Let me buy myself a little more space. All right, so what do we need to start by doing? What's that? Okay. I don't think we can say that yet. Not yet. So you can't really talk, you can't really like declare whether or not you have pivots until you start doing what? Go ahead. This is not reduced at all. So we have to do that first. So let's work towards that. How can we start reducing this thing? Go ahead. Subtract row 1 and row 2 from row 3. Yeah. Okay, so your objective is to put a 0 where there's 3s. Okay. So when we're reducing a matrix, what's our first goal usually? In this case, I think it would happen to us for free. Get a 1 in that top row, right? So let's think about it this way. I would really like if I could have a 0 here and a 0 here. What are two operations I could do to make that happen that I can kind of do at the same time? Go ahead. So row 2 minus row 2? Then the whole thing would go to zeros. That would make them zeros, but now would lose all that information. Row 2 minus 2 row 1. If I do row 2 minus 2 row 1, and put that back into row 2, what's a similar move I can do with row 3? Right. So this is one of those kind of, I think I talked about this last time. This is always going to be available to you. You can use the first row to basically clear everything out below it. Go ahead. I think you're right. So let's see what happens when we. So that is the case. So what would you expect of this if we start reducing this matrix? Where would that be? Okay. All right, let's make sure. So top row is 1, 1, 1, 2. Second row is -1, 1, 1. They both look like that? Okay. So where can I go from here? Is that legal? Well, I mean, effectively, if you look at you subtract a row. So we thought we had 3 equations, right? What did we really just learn? We have 2. One of them is just rehashing the same information as the first 2. Let's put this another way. Let's say I didn't notice that at all. What will my next move be here? Because we got a 1 in the now we have a 1 as a pivot right here, right? 0 is below it. What would our next goal be to do? Okay, how would I do that? Multiply, so negative row 2 goes to row 2. So 1, 1, 1, 2, 0, 1, -1, -1. And then from there, what should we do? So now we're in column 2. We have basically we got our pivot where we want it. So what should we do with that pivot now that we have it? Add row 2 to row 3. Row 2 plus row 3. Row 1 minus row 2. goes to row 1. So because of what was pointed out about row 3, it goes away. And then what does row 1 become? 1, 0, 2, 3. All right. How are we doing with reducing this thing? What's next? Yeah, we're done reducing. Because so here's a pivot for x or x1, pivot for x2. Is there any chance I'll get a 1 here? Not without backfilling those. So yeah, we have two lead variables, which are x1 and x2. And we have a free variable, which is going to be x3. So what can I say about x1? What's x1 equal to? 3 minus 2x3. And x2 is equal to? -1 plus x3, right? Okay. And x3 equals, let's write the plainly obvious, but I have seen both of these. I'm not sure which one Infinity likes more. One where they just keep x3 as a parameter, and one where they rename it as something else. In reality, they're equivalent, but depending on how Infinity got coded, it might prefer one or the other, but these are essentially identical. I'm just renaming x3 in one of the cases. How are we doing? Any questions before we leave this chapter? All right. Okay, so moving on to chapter 2. So far we've kind of talked about matrices as basically just a way to talk about equations. Chapter 2 basically treats them like they are their own objects. You can kind of operate on them independent of trying to solve equations. So that's what we're going to do now. So the first few sections here, you know, basically going back to arithmetic, matrices are not like, they don't act the same way as real numbers do. So we kind of got to rehash some of the arithmetic stuff. But let's talk about some things first. Are these equations true? Let's just stick with the top one. Is that top equation true? Or do you need more information? What do you? So if y equals 2, so you're saying yes if I meet these conditions. Okay. Is there any other conditions under which those are true? Okay. Do they both have to be true or just one? What do you think? Okay. So I admit I'm kind of like, I have not, right now I'm looking for your thoughts because I have not told you like what the conditions are. Right now I'm kind of putting you on the spot. So if y equals 2 and x equals 2, where'd those come from? Like, why did we say those conditions? That'll be 3. Okay. Right. So you're corresponding the entries together, right? And then it looks like by default, x squared will equal 4, right? What about if x equals -2? Does this work? I think that the top left corner will work, but that's about it. So it sounds like you're assuming that for these equations to be true, every single corresponding pair of entries has to be equal. Okay. Then I think I know what you'll say about this next one. So you said yes if these are met, right? How about the second equation? Why not? So there's no conditions of x and y that we can have to save that one, right? What about the third one? So you're saying no? Oh, okay. You're saying so you're saying it's the same conditions. Yes, if x equals y equals 2. How do you feel about that? Okay. We're going with these answers. What's the penalty for being wrong? Absolutely nothing. Don't worry about it. So let's see how we did. So let's talk about some properties of matrices. And we've organically talked about some of these, but the order of a matrix is basically another way to talk about the dimensions. So what I was talking about is m by n. So number of rows comes first, number of columns comes second. A 5x4 matrix has 5 rows, 4 columns. And by default, it has to be rows first, columns second. The elements are basically the entries that live in each cell of the table, essentially. And the way we index those is by this like double subscript. So if I write something like that, it's the element that lives in the 5th row, 2nd column. Beyond just like plucking out the individual elements, we can talk about vectors, which usually are the columns, the individual columns of a matrix. All right, when are they equal? They're equal if and only if every corresponding pair, like basically 2 matrices are equal if this element is equal to the element in the same place in the other matrix. And that has to be true for every single element. So how do we feel we did for this set of 3? Go ahead. What's that? That's the one I'm going to push back against. What is B31? Assuming this is B. This is A. 0. What is A31? Doesn't exist. So because of that, for matrices to be equal, they have to be the same what? Same size, same order, at the very least. If they're not, then we can't even ask that question. How are we doing so far? Okay, something else I haven't told you how to do, but I'm just going to see how you do with it. Any wild guesses on what happens with this top bullet? Okay, a new matrix. How big is the new matrix? What's the order? 2 by 2? Okay. What goes in there? How? How do we do that?
Added based on their position.
Okay. Right, so going position by position, adding the corresponding elements together, right? Is that something you've done before? Probably. Okay. Hope so. What about this next one? something else I haven't talked about. What do you think? So again, a 2 by 2. Okay. So how'd you get all those? So scalar multiplication. Multiplying a number by a matrix makes a matrix. What's the result going to be here? A 1 by 2. Yeah, how big are the matrices involved in this? They're both 1 by 2s. All right. So all right, so what's the left entry going to be? -4. And -4, 0. And how about this last one? We're not doing it. Why not? They're not the same order. Yeah, what's the order of 1, 3? 1 by 2. And what's the order of 2, 2? 2 by 1. Okay, so different order. We're saying we can't deal with those at all. Is this something you've done before? Okay, so even though matrices and real numbers are not identical things, a lot of things work the same way. So matrix addition, yes, the way you add two matrices together is you add the corresponding entries together. So for every ij pair, add those elements together. It's only defined if A and B are the same order. Scalar multiplication works exactly the way that many of you seem to think it was. So if you're multiplying a scalar, a real number, by a matrix, just multiply that real number by every single entry in that matrix, and that becomes a new matrix. How big is that new matrix? Or what's the order of the new matrix? Whatever it was, right? And just like you've always done, multiplication is more important than addition. Carry that out first. All right, how are we doing? All right, can we find some solutions here? What do I do? Multiplication first, so what is that going to give me? Okay. Okay. All right, if I add those together, I get x squared plus 2y, x cubed minus 4x, 2y, minus x plus 2z. Okay, so it looks like everything we've done so far deals with the left-hand side, right? So still want to know what x, y, and z are equal as far as I can. So where can I go from here? Go ahead. Move them all to one side of the equation, then do what? Okay. Actually, I don't know if I can. I think an augmented matrix I think I need to have constants. I think I need to have a column vector on the right-hand side here for that to. There's something else I can do though. Go ahead.
Assume that like actually let's say like
Why'd you say x equals 0? Well, why don't you think this is true? I think that is absolutely true. I think x cubed minus 4x equals 0 is totally fair to say. Why? So basically, this left-hand side here, we just turned this into this, which means that if I take the corresponding entries from one matrix and set them equal to the corresponding entries from the other matrix, that's totally fair to do. So entry 1, 2 of both matrices, those better be equal. So x3 minus 4x better be equal to 0. Which from there, I can say some things about x, right? What's x equal to? Partly. So if I factor in x, I get x times x squared minus 4. So I get x equals 0, 2, minus 2. Go ahead. Yeah, that's part of. Yeah, so we have to find a bunch of stuff that. Yeah, that's right. So we're going to find a bunch of conditions that I'll have to match. So these are 3 candidates we got from X, but these just come from that one pair. We might find that other things are inconsistent. So for example, the first one of these I showed you, x squared equals 4, that would have given us x equals -2. But we threw that out because that doesn't fit with x plus 1 equals 3. So we'll get a bunch of different conditions, but if some of them contradict, we can't keep them. All right, so what other conditions do we have? What's that? X squared plus 2y equals 8. What can I say about y then? I can plug in my x values. So if x equals 0, what is y? Y equals 4. If x equals 2, I don't think it matters if it's plus or minus 2, right? Then y is equal to 2. All right. So I think I have some conditions for x and some conditions for y. What about z? Negative x plus 2z equals 0. So I have conditions for x. Again, I can kind of run through them. If x equals 0, then what's z equal to? Yep. If x equals 2, then z is equal to 1. And if x equals -2, z equals -1. So we looked at 3 of the pairs of entries. We didn't look at the other one. Would it give us anything new? No, it says 2y equals 2y essentially. There's no way to fail that. All right, so what are our possibilities here? I think I have a lot. So if x equals 0, then what can y be equal to? 4. And Z is that the only possibility of x is equal to 0? I think it is. Because if x is equal to 0, then we get a single value of y and a single value of z. So I think we can kind of look at this as x driving everything. What about if x is equal to -2? Then what's y equal to? 2. And what is z equal to? -1. If x is equal to -2, and then what about if x is equal to 2? 2, 2, 1. I think that's the full range of possibilities. Questions? Complaints? Okay, so another thing we can do with matrices is called transposition, finding the transpose of a matrix. Basically, what a transpose of a matrix is, you take all their rows and rewrite them as columns and vice versa. So let's do a generic 2 by 2. If this is A, B, C, D, and this is A, then A transpose is this A superscript T. What would this transpose look like? Well, it's top row. Basically, row 1 is top row, right? Row 1 is going to become column 1. Where does column 1 go? Vertically, but where? Yeah, column 1 is the far left. So AB, and then row 2 is CD. That becomes column 2. So if A has an order of m by n, what's the order of A transpose? N by m. So if I'm changing the rows for the columns, then I'm going to change their numbers as well. So for a square matrix, you don't get a new size matrix, but in general, a transpose is not the same size. What's the order of this? What do you mean go back to how it was? Yeah, so if this is A and this is A transpose, what is A transpose transpose? In general, that's always true. So transposition is this reversible situation. The transpose of a transpose is always whatever matrix you started with. All right, so how would I do this thing? Okay. Okay.
Zero.
Just like that. Yes. Well, let's do this. So I think you distributed that negative sign. Actually, I may have heard you wrong, but I think this is okay now. Are we okay now? Question? That's a very good question. So yeah, do we miss this? Does it matter if you do the transpose first or do the multiplication? Certainly not in this case, right? It does feel a little weird though, right? What about if I did the addition before I did the transpose? That would absolutely change some things. If I add 4, or if I add -8 to -3, that would be a problem because that's not the thing I'm supposed to be adding to -8. So what do you do in scalar multiplication? You multiply the scalar by everything inside the matrix. So I don't think it matters if you multiply everything in that matrix and then move them around. But for addition, I think that would fundamentally change whatever your answer is going to be. Having said that, what should I do now? Transpose. What is the right-hand matrix going to look like after it gets transposed? One way that I've commonly seen to think about transposes is this: if you draw this diagonal and then basically just reflect everything over it, keeping everything on the diagonal where it is. That's another way to visually think about transposition. So what gets reflected in a 2x2 matrix? It's just whatever's here and whatever's here. Those are going to change places. Everything else is going to stay where it is. All right, now what? Add them together and I get what? Question so far? All right. Okay, so look back to equation mode for a second. Let's reduce this thing. Give myself more room to do so. All right, want to reduce this thing? What should we do? Go ahead. Okay, want to get a 1 there? How would we do that? So row 1 minus row 2. Put that back into row 1. All right, row 1 minus row 2 is -1, -1, -2, -2. And then you wanted to negate that. Excellent. Now what? Job 1 is to get our first pivot, which I think we got. What are you going to do now? Row 3 minus 3, row 3? So row 3 minus 3 row 5. Oh, sorry. Okay. Row 2 minus 3 row 1, that goes to row 2. Let's do a corresponding move to row 3. Row 3 minus 5 row 1. All right, so row one didn't change. 1, 1, 2, 2. That better have happened. So row two minus 3 row one, that should be 1. Negative 8, 3. Please double check me. Don't just write down what I'm doing.
On row 3,
Yeah.
13, that's supposed to be positive 2.
Probably. Let's find out. Row 3 minus 5 row 1. 7 minus 4 times 5 is 20.
That's what
Yeah, that's why none of this works. I did that whole thing messed up. All right. 2, 6 minus 10 is negative 4. And then 20 minus 10 is 10. That feels better. Is it good now? Cool. All right, now we got our second pivot. Now what should we do? Actually, I don't think we were trying to get our second pivot, were we? I think we just got it by chance. Just happened. Cool. Now that we have it, what should we do with it?
the 0.
Get the zeros around it. So I think we can choose 2 operations to make that happen. Give me one of them. Go ahead. Go ahead.
Can we, I think first we should divide, we should scale row 3 by
Okay. All right. If we scale, we'll have. I just wrote 3s everywhere. Okay. That's what I wanted to do. I heard you. I understood it. Okay. That was good. All right. From there, what should we do? Go ahead. Row 3 minus row 2. And put it back to row 2. 3. Okay. All right. That's one thing we can do. Row 1 minus row 2 to row 1. Okay. So row 2 is not going to change. 0, 1, negative 8, 3. Row 3 minus row 2. So 0, 0. What's that? Yeah, I did the operation in the wrong place. Row 3 minus row 2. I put the right numbers in the wrong spot. Row 3 minus row 2, 0, 6, 2. And then row 1 minus row 2. 1, 0, 10, negative 1. Literally, we're going to get a unique solution, right? Not what I wanted to happen. Yeah, I wanted to show you how to parameterize these things, but this is not, I thought that I put one in here that was going to have infinitely many solutions. I thought it was going to, but I don't feel like we did anything wrong. If we did, I'm not seeing it. All right, sorry, I'm going to throw this one out. Let's replace it with one. Let's pretend to reduce it to something that didn't reduce to echelon form. So 1, 0, 2, 6. So yeah, the thing I wanted to show you here is there's an alternate way of showing the parameterization, things like this. I really thought that matrix was not going to have a unique solution, but I'm not seeing the error in it. All right, so based on what we've done before, how would we parameterize what we have?
X2 equals -9
X2 equals -9 minus 4x3.
X1 equals 6 minus 4.
X1 equals 6 minus 2x3. And it sounds like x3 is the free variable. Okay, so, and this is what we just did, right? This would be, very compact, but it's a totally legitimate way to give the solutions to that system. The other one I wanted to show you is this. Is this what we call expanded vector format. So in general, the thing we're trying to solve for these equations is trying to solve for that column vector that has all of our variables in it. So x1, x2, x3. So what are our constants here? So what I would like to have is this. Something of this form. This solution is equal to some matrix plus a parameter times another matrix. I just have one parameter, right? Okay. So what matrix, what am I going to fill in for these two column vectors that I just wrote down?
First column is 9, 6.
You're very close. They're written down in they're written down in a counterintuitive way. But 6, -9, 0 is good, right? How'd you get that? Yeah, those are the constants that come from the solutions, right? X1 equals, so basically this vector right here is, I'm not multiplying this by anything. This one here, I'm going to multiply by some parameter. Basically, what's that parameter t doing the job of? That's x3. So then what am I going to multiply that parameter by? -2, -4, 1. So let's expand this out again. What does each row of this thing say? 6 minus 2t, -9 minus 4t, and t. Does that fit with what we wrote down above it? As long as you write it in an order that makes sense. So this right here is the expanded vector format. And basically you could have any number of these column vectors, but that'll be dictated by how many parameters you have. So in general, what these look like is this. Basically your solution's equal to this. You have a constant vector, and then a bunch of column vectors times scalar parameter column vector times scalar parameter. And there's no theoretical limit to the number of parameters you might need. So as many as get the job done. Questions? I think I have maybe one more. Man, I was really confident that was going to work out. It doesn't. Actually, I bet it does. We'll find a mistake later. All right. Any other questions about this section before we leave it alone? Okay. So a lot of arithmetic in matrices acts just the way you'd like it to. So let's talk about stuff that doesn't act the way you want it to. So matrix multiplication. Is this something you've done before, is multiplying matrices together? Okay. I think I won't say it's easy, I won't say it's hard, but I will say it's deeply not intuitive. So a couple questions to get you started here. When you're multiplying real numbers, under what conditions does that product exist? Under what conditions is that defined? Or under what conditions is it undefined? Have you ever even thought about this? You multiply two numbers together and you get nothing back. When does that happen? I'm just talking about real generic, just numbers. I'm not even at matrices yet, just numbers. One by one matrices. What's that? What's 0 times 10? That's well defined. Is it ever undefined? It's always defined. Always, always, always. There's no such, if you have two real numbers, their product is always a thing that exists. Does the order matter? What's 5 times 9? Is that the same as 9 times 5? Is there any two numbers that you could switch and change the answer? So in multiplication, always defined, and it's commutative, meaning I don't care if I move the numbers, the result is identical. Go ahead. That's not true. So I got 5 different matrices here. Which of them could I multiply? Like I said, I think this is like deeply non-intuitive. Like, so for example, could I multiply A by B? Why not? Doesn't feel right. Why doesn't it feel right? Okay, they're not the same order, right? Go ahead. C by D. What's the order of C? 2 by 3. What's the order of D? 3 by 2. Are those the same? Clearly not. Yeah. With the gestures, I agree. So yeah, it's like basically what you said is I can do one thing times the other, which is exactly how you multiply matrices together. You multiply a row by a column, which sounds totally arbitrary and nonsense, but I will tell you, yes, C times D exists. Can I multiply D times C? No. Obviously not. So it's like all doing this all to point out that like so much of this is deeply non-intuitive and deeply not obvious. But I will highlight is this: when you multiply matrices together, basically what you're doing is this. Do you remember taking dot products of vectors? So the way you take a dot product of a vector is, let's say I have vectors A and B. A is equal to 1, 6. B is equal to 2, negative 4. What is A dot B? It's equal to 1 times 2 plus 6 times negative 4. Basically, you go component by component, multiply the corresponding pairs together, and then add up all the things you got. That is the identical process you do with a matrix, except that vectors are simpler. They're one-dimensional, right? You can either think about them having one row or one column and then just a bunch of stuff in it. Matrices are two-dimensional. So the way that matrix multiplication works is I multiply a row by a column. So what do I need to be true about a row and a column? Sorry, a row from the left matrix and a column from the right matrix. Go ahead. The number of rows from column A is equal to the number of columns from matrix B. That is why CD is a product that exists. And I think I just lied to you. I think I should have said it the other way around. It's the number of columns from matrix C that has to be the same as the number of rows from column D. CD works. DC does not. E times D. What's the order of E? 3 by 1, right? E times D, I don't think works in either direction. What's the order of B? 1 by 3. So what I'm telling you is that let's talk about BE and EB. Actually, these are really small, so I'll put them side by side. What does BE look like? It looks like 3, 1, negative 4, and 1, 2, 3. So what I said I wanted to do is I want to multiply a row of the left matrix by a column of the right matrix. Does that work here? Multiply this row by that column. So there are 3 things in the only row this left matrix has. There are 3 things in the only column the right matrix has. How many times am I going to be able to do that? Once. So when I multiply a 1 by 3 matrix by a 3 by 1 matrix, it makes a 1 by 1. But what happens if I try to do this the opposite way? If I try to multiply a 1, 2, 3 by a 3, 1, negative 4, what's the order of the thing on the left? I just found out I lied to you again. What's the order of the thing on the right? 1 by 3. That works. So can I multiply a row of this matrix by a column of this one? Yeah, they're both just single entities, right? How many times can I do that? Like, how many combinations will there be for me to do that? So I would multiply this row by each of those 3 columns. And I could do that with each one of these elements, right? So multiplying a 3 by 1 by a 1 by 3, that yields a 3 by 3. Okay, can I put some like generality behind it now for you? Go ahead.
So like if that one works, then how come DC doesn't work with the 3 by 2 times 2 by 3?
I'm starting to think I lied to you about that one. Yeah, they both work. So C by D, or CD is 2 by 3 by 3 by 2, right? Yeah, these both work. I'm very sorry. So CD gives you what size? 2 by 2, and DC gives you a 3 by 3. So why am I saying all this? Let's put some generality behind it all. So let's say I have two matrices. A is M by N, B is P by Q. The only way the product exists is if N equals P. Have any of you ever worked with MATLAB much? There's an error that I used to get with, I learned MATLAB before I ever learned how to deal with matrices at all. And I used to always get this error that said inner dimensions must agree. And I never knew what the heck it meant until I took a linear algebra class. But that's what this means. So you're multiplying M by N matrix by a P by Q. This product only exists if the inner dimensions are the same number. If the inner dimensions are the same number, the outer dimensions give the order of the matrix.
But wouldn't that have meant that it would have worked in another way?
Yeah, I think I was wrong the first time, but I got corrected and I corrected it. Yeah, C and D work both directions.
Well, if 1 times 3 and 3 times 4.
Yeah, those work both directions too. So what on here doesn't work? Let's go back to it.
Anything that has
So let's just go kind of, we only got 3 minutes left, so let's do this. Let's find out which ones of these exist, and then we'll do some of them tomorrow. What can I multiply A by? A times C, right? So A is what order?
2 by 2.
2 by 2. And C is what?
2 by 3.
2 by 3. So AC exists, right? Does CA exist? No. A 2 by 2 times a 2 by 3 is fine. A 2 by 3 times a 2 by 2 doesn't work. Go ahead. No, I want AC is fine. So we won't actually do this, but let's end with like this comparison. So 2, negative 3, 1, 6 times 1, 0, negative 4, 7, 2, 1. So basically the way that matrix multiplication works is I multiply a row from the left matrix by a column from the second matrix. So if I take a row from the left matrix, those always have 2 elements in them. The column from the right matrix always have 2 elements in them. So, but what happens if I look at CA? CA is going to look like 1, 0, negative 4, 7, 2, 1, 2, negative 3, 1, 6. Multiplying a row of this matrix by a column of this matrix, those aren't the same length. So I won't be able to do those products. So that's why AC is fine, CA is not going to happen. So AC is one we can multiply out tomorrow. Will A multiply by anything else?
Yeah.
DA should work. What's the order of D?
3 by 2.
3 by 2 will multiply by a 2 by 2. I think those are the only 2 that involve A. So yeah, I got 2 10s. So we'll make a more complete list tomorrow and we'll work on some of those.